Although the vertex form is potentially the easiest form of a quadratic to graph, we still spent time in our last video learning how to graph quadratics in the standard form because of the lessons we could learn from that process. A similar rationale will apply to graphing quadratics in the factored form. Despite being able to easily convert this form to the standard form and maybe even convert to the vertex form from there are still lessons that we can learn from considering the factored form on its own. Additionally, there will be something special about the inputs that are easiest to evaluate, and this special aspect of the factored form will lead us to one more important feature of quadratic functions. So let's explore graphs of the factored form and learn about zeros of quadratic functions. Let's start things off with this function that is indeed in the factored form. If we make an extended table of values for this function, it would probably be easiest to have a column for each factor so that our final output can just be calculated by multiplying each factor. Then, we need to choose some inputs. We'll start with 0, like we did regularly with the standard form, and see that we get an output of -8. We chose 0 as our starting input because our initial strategy for graphing quadratic functions in the factored form will again focus on choosing inputs based on convenience. However, there are a couple other input values that might be even more convenient. If we pick 4 as our input, then 4 minus 4 is 0, and at this point, it doesn't even matter what the other factor is. If one factor is 0, then the output is guaranteed to be 0. We can follow a similar process with our next input by noticing that -2 plus 2 also yields 0. Thus, plugging in -2 will give an output of 0. You may notice a connection here with our process for solving quadratic equations using the factored form. If we set our function definition equal to 0, then we can solve the resulting equation this way. These solutions are the same numbers that we just used as inputs in our table, which is why we got 0 as the corresponding output values. From there, we can graph these 2 points and make an observation. When we graphed the standard form, we ended up realizing that it was most convenient to locate the vertex point first and then plug in values around the input coordinate of the vertex. Here, we clearly didn't start with the vertex, but once we have these 2 points, it's rather easy to find the vertex. Since we know that parabolas are reflection symmetric, we know that the axis of symmetry falls exactly halfway between 4 and -2, which ends up being the line where x equals 1. And once we have that axis, we can use 1 as the input to determine the location of the vertex. After locating the vertex, we can continue plotting points along with their reflective pairs, and eventually we'll get this graph. One thing to note before moving on, though, is that we have a special name for our main 2 inputs. Since the inputs of 4 and -2 gave us outputs of 0, we call these inputs zeros of the function. These inputs are also called roots at times, especially in the context of polynomial functions. We'll stick with calling them zeros for now, though, and these zeros will form the foundation of our strategy when graphing the factored form. For another example of this process, let's look at this function. Here, our zeros will be -8 and -5. Then, we could determine the location of the axis of symmetry mentally, but if we want to formalize that process a bit, we just need to take the average of our zeros. This involves adding our zeros and dividing by 2, which gives us the value of x for our axis of symmetry. Next, we can find the vertex of the graph by using the location of our axis of symmetry as the input to our function. From there, a few more input values will give us a good picture of the graph, and we can finish off with this parabola. Our next example will include a different leading coefficient. If you think back to our general forms of quadratic expressions, we wrote the general factored form this way, where we can think of a as an additional constant factor. Now, a has been 1 in both examples we've done so far, which is why we ignored it. This time, however, we'll need to make sure that we take a into consideration. Thus, we'll include an extra column in our extended table to show that -2 is a factor of the output each time. Fortunately, this doesn't change our strategy that much, if at all. When we plug in 3 and 7, we still get a factor of 0, which means that the final output will still be 0. Plus, the calculation for the axis of symmetry will still be the same. The only real difference is that when we find the vertex and a few other points that aren't zeros, we'll need to multiply by -2 in addition to multiplying our linear factors. Then, we get this parabola, which allows us to see that a negative value for a once again results in the parabola opening downward. Now, while the general factored form was officially this expression, there was another version of the factored form that showed up regularly. While this function definition doesn't fit the official factored form, we decided that it still counted as the factored form, so we should make sure we know how to graph it. The main difference here is that it's going to be a bit harder to intuitively know the zeros of our function. But if we set the individual factors equal to 0 and solve from there, we can see that the zeros are going to be -9/2 and +5/3. And while these aren't the simplest zeros, they are still zeros nonetheless. From there, we'll still calculate the axis of symmetry and draw that, but we might actually avoid finding the output for our vertex, since that will involve meticulous fraction calculations. Instead, we can use some inputs near the vertex to get an idea of where this parabola goes. We'll quickly see, though, that some important parts of the parabola end up being way outside the graphing area. When we encountered this issue with the standard form, we simply moved our viewing area to focus on the vertex, but we kept the scale of our axes the same. In this case, however, we'll do things a bit differently. Since zeros are such an important part of our understanding of factored form graphs, we kind of want to keep these zeros visible in our graphing area in addition to showing the vertex area. Thus, we'll actually leave the x-axis at the same scale while adjusting the y-axis to give it enough range to show the vertex and the zeros. Once we do that, we're able to plot the points that we found previously and draw our parabola. One final note about this example is that the process of finding zeros can actually help us rewrite this function in the official factored form. We know from our graphing process that -9/2 and +5/3 are zeros of the function, so the linear factors of this function can be expressed in this way instead. From there, we can see that these two expressions aren't actually equal yet, but we also know that there's an a value that we can include in this expression that will make these equal. And finding that a value is easy enough. If we did the first step of the distribution process for these two original factors, we would see that we get a quadratic term of 6x squared. This means that a is 6, and if we include that in our rewritten factored form, these two expressions are now equal. We can check our work on this in a number of ways, and one easy way is to convert both of these expressions into the standard form to see that their standard forms are equal. However, a more elegant method is to start with this expression and manipulate it to get our other expression. To do that, we'll rewrite 6 as 2 times 3. Then, if we pair the 2 with the first linear factor and distribute, and do the same with the 3 and the second linear factor, we can quickly see that we do indeed get our original expression. This helps illustrate how finding the zeros of a function can be a way to help determine the official factored form of the function. With that, let's do a couple final examples of graphing the factored form. We'll avoid making our axes for a moment until we know more about this function, and instead we'll note that we have 2 identical factors, which in turn means that the function only has one zero. This singular zero can only happen for quadratic functions when the vertex is on the input axis, and because of this, we should be able to use our standard set of axes for this example. Then, once we complete our axes and plot our combination zero vertex point, we can draw our axis of symmetry through the vertex, plot some additional points with their reflective pairs, and complete our graph. For our final example, let's consider this function. We'll once again hold off on making our axes for a moment and instead locate our important points using zeros and the axis of symmetry. Once we find our vertex point, we can see that we'll need to change the scale of our output axis in order to fit the vertex point. And by plugging in a few more numbers in our table, we can decide on a reasonable scale and draw our axes. Then, we'll draw our axis of symmetry to help with identifying reflective pairs before plotting the points that we identified. Finally, we can complete the problem with this graph, which gives us a great snapshot of the function. When we've worked with the factored form in the past, we've noted multiple times that the factored form is limited since only a select few quadratics are nicely factorable. In our graphing efforts, however, we were able to more explicitly establish a connection between the factored form and the zeros of a function. While we've been using this connection so far to find the zeros of each function given the factored form, we could just as easily go the other way and use the zeros of a function to find the factored form. Because of this link, we'll finish off this video with a couple examples of this process that allows us to convert any quadratic expression into the factored form. First, let's consider this function, which we actually already looked at in one of our videos about converting to the factored form. In that video, we initially tried factoring by looking for pairs of numbers that multiplied to -20 while adding up to 4. Eventually, the actual factored form was revealed to be this. But how is that answer determined? Well, if we set this expression equal to 0 and solve, we'll find the zeros of the function, which will allow us to find the factors. So, how do we solve this equation? Well, we have a new tool available to us that we didn't have when we initially looked at this function: the quadratic formula. By applying the quadratic formula here, we can see that in order for our function definition to be equal to 0, x must be -2 plus or minus 2 times the square root of 6. We'll split that into 2 component solutions for x, and then we'll write our factored form as x minus m times x minus n, where m and n are the 2 solutions we got. Now, having parentheses within parentheses can be a bit annoying here, and we can resolve that by distributing the negative sign. But once we do that, we can see that this matches the factored form that was presented previously. Of course, at this point, we should probably check our work by distributing, and that will be a pretty laborious process. Still, we'll show that process here, and eventually we'll see that this factored form is indeed equal to the original function definition. We'll check out one more example of this process that has a couple key differences. If we had tried factoring this function previously, we would have said that it was not factorable. However, we now know that we can determine the factored form by finding zeros. So let's find those zeros by using the quadratic formula again, and eventually, we'll get these solutions. Notice this time, though, that our solutions are not real numbers. Instead, they're complex numbers with an imaginary component. This is why we previously said that this was not factorable, because it truly is not factorable over the real numbers. However, now that we know about imaginary and complex numbers, we can still factor this expression in a way. Sure, that factorization will involve the imaginary unit, but this is a legitimate factorization over the complex numbers. There is one extra aspect to be careful of, though. Note that the original function definition contained a leading coefficient of 2. Thus, we also need to include an a value in our factored form. Once we do that, though, we do indeed get an equivalent function definition that's in the factored form. We'll once again do the proper distribution to verify that this is the correct factored form, and once we do that, we'll see that we were spot on. This is how we can factor quadratic expressions that don't have nice numbers. And with this knowledge, we should now be able to factor any quadratic expression. That concludes this video on graphing quadratic functions in the factored form. Hope you learned something new, and thanks for watching.